Well, students, we have finished the first chapter of our notes, which is on mathematical preliminaries, and we are into the second chapter, which is on errors. This is the first topic of our course. As I told, numerical analysis is all about finding methods that can give approximate solutions to our mathematical problems, and these methods are those which can be implemented on the computers. You may be surprised that before introducing any methods, what is there for us to study errors? Because once we understand certain methods, then only we can see what is the error that the method commits in getting the approximate solution of a problem, right? Before introducing any method, we are directly jumping into errors. This may look a bit unusual, but there is an important point to be remembered before going into the development of any numerical methods. This is nothing but the error committed by the computer because of the floating point approximation. Let me give you an overall picture of how this error occurs. As I told you in the first lecture, we have a mathematical problem. Given a choice, we would like to get the exact solution of the problem through some method which are generally called direct methods. But if we are very particular that we will only solve those problems for which we know direct methods to get exact solutions, then most of the time we will be either not solving the realistic problems or we will be solving a oversimplified problem which may not be of significant interest. So often we have to go for approximation. Numerical approximation is very popular because they can be implemented on a computer. But when you go to implement your method on a computer, what we do is we first develop an algorithm for the method, and then we write a computer code for that algorithm and implement the method on a computer. Now, when we execute that code, what the computer does is it gives you a solution which is basically in terms of numbers. It's called numerical solution. But the method as such, if you see, it is just coming as an approximation to our original problem. Therefore, mathematically, we are committing certain error in devising this method, right? For instance, if you have a function f of x, instead of working directly with this function, I may be comfortable in working with the Taylor polynomial of that function, right? So therefore, there is naturally an error committed in my calculations because I'm not working with the exact function, but I'm working with the approximation. That is what in the last class we have seen as the truncation error. That is one type of error which came out in this approximation. Generally, in the process of approximating a mathematical problem, we commit certain errors when we are devising the method, which we call as the mathematical error. Like one particular example of the mathematical error in this particular situation of approximating a function by Taylor polynomial is a truncation error. Apart from this error, we are also going to commit certain error when we put the method on the computer and get the numerical solution. That error is called the arithmetic error generally. How this arithmetic error comes is, well, since the computer has only a finite precision memory, it cannot store a number with infinite digits. For instance, if you want to store the number 1 by 3, on a computer, it cannot store it as 0.333 and it keeps on going. A human being can understand what it is, but computer has to stop at some finite number of digits, and it can only take this number with finitely many digits, and thereby it is not exactly considering the value of 1 by 3, but it is only taking approximate value of 1 by 3, right? So in your calculation, your computer must be using approximate value of each number that is involved in the calculation, and therefore your final solution that comes as your approximation to the original problem is going to be not exactly what a human being can calculate the numbers using the numerical method that you devised. Okay, it will be slightly different from what a human being can compute, because human being can compute it 1 by 3, right? This is just an example. Whereas a computer has to use this number in the place of 1 by 3 and it will be calculating the solution. There's one more level of error which is committed in this calculation, that is called the arithmetic error. So summarizing, if you see, you want to solve the mathematical problem and get exact solution. In case if you don't know a direct method, then you decide to go for a numerical method. So when you devise a numerical method, you are putting some approximation or the other to devise this numerical method. Thereby you are committing mathematically some errors. That is what is called the mathematical errors. Okay. So if you take this method and solve by yourself without putting any error in the numbers that you are dealing with, then you will get the approximate solution that involves only the mathematical error. But when you go to implement it on a computer and get the numerical solution of it, because your computer makes certain errors due to its limitation on storing only finitely many digits in the number, it also brings in a new type of error which is called the arithmetic error. Therefore, if you see the exact solution minus the numerical solution, that is the solution which is given by your computer after running your code, that is actually called the total error. So the total error is therefore the sum of the mathematical error and the arithmetic error. And your exact solution is nothing but your numerical solution plus mathematical error plus the arithmetic error. In this chapter, we will see what is called the arithmetic error and how dangerous it is if we just neglect this part. Of course, mathematical error one has to study depending on what method we use for what kind of mathematical problems. Whereas arithmetic error is something which is common, because any method that you implement on a computer, you are going to get this arithmetic error, which is not going to be method dependent. Perhaps it may be depending on the computer that we use. So in this chapter, we will see how this arithmetic error comes and how to handle them. As a first step, let us understand how a computer stores numbers in its memory. For this, we will introduce a notion called floating point representation. Let beta be a natural number which is greater than or equal to 2. Then any real number can be represented exactly in basis beta as minus 1 to the power of s into point d1, d2 up to dn plus 1, like that it goes on to the base beta. This is just a symbol into beta to the power of e, where di's are some numbers between 0 to beta minus 1, with the important condition that d1 is not equal to 0. This is very important. Or if you want to represent the number 0, then all the di's are 0. It means either d1 is not equal to 0. If d1 is equal to 0, it means all the di's are 0 and we are actually representing the number 0. S is either 1 or 0 and is called the sign. So this S is responsible for denoting what is the sign of the number. E is an appropriate integer called exponent, and this, called the mantissa, is actually written as this expression. The number beta is often called radix, which is also called the basis. The representation 1 is called the floating point representation of any real number x. Let's take an example with beta equal to 2, in which case we call the representation as binary representation. It means you have 2 to the power of some e. Okay, so this is just to indicate that our representation is with base 2. Similarly, if we take base 10, we call it as decimal representation. Generally, human beings work with decimal representation, whereas computers work with binary representation. There are also other representations which we will not go into the details. I hope you all know it from your school time. Even in our numerical analysis course, we will never touch upon the binary representation. We will always work with the decimal representation. As I told you in the first slide, a computing device stores a real number with only a finite number of digits in the mantissa. That is, in this part, a computing device, whether it is a calculator or a computer, it cannot store digits which are infinite in number. Means it goes on. It has to stop somewhere up to finite number of digits in the mantissa. So when we have only finitely many digits in the mantissa, we call such numbers as n-digit floating point numbers, where this n is nothing but the number of digits that are there in the mantissa. Let's take an example. Take the number x equal to 6.238. How will I represent this number in the floating point representation? Well, you have to have the mantissa in this form. So if I want to write the mantissa in this form, remember the important point is that d1 should not be equal to 0, right? So with that condition, the mantissa of this number is 0.6238. Now, if you want to bring it to 6.238, then you will have to multiply it with 10 to the power of 1. Why 10? Because it is the decimal representation. Generally, we don't write that base 10 notation when it is decimal representation. And since it is a positive number, we choose s as 0. And therefore, the representation is -1 to the power of 0 into 0.6238 to the base 10, which generally we don't write, into 10 to the power of 1. This is the decimal representation of this real number. So s is 0, beta is 10, e, that is the exponent, is 1. Whereas in the mantissa, we have d1 equal to 6, d2 equal to 2, d3 equal to 3, and d4 equal to 8. Let's take another example. X is equal to minus 0.0014. Why I took this example is because there are some leading zeros after the decimal point, right? So let us see how to write this number. Since we have the condition that the first digit in the mantissa should not be equal to 0, we have no choice other than putting 1 as d1 here, and then the other terms comes d2, d3 and all will follow as it is there in the number. Therefore, we have to have the mantissa as 0.14. Now, in order to bring 0.14 to 0.0014, therefore, we have to multiply it by 10 to the power of -2. So this is how the exponent is fixed. So that's the only tricky part. You have to make the mantissa in such a way that d1 is not equal to 0. And correspondingly, you choose your exponent. The sign part is very easy because it's a negative number. Your s is 1, right? Note that in the above example, there are only finitely many digits in the mantissa. That is because the original number itself had finitely many digits. So these are n-digit representation. This is 4-digit representation. This is 2-digit representation, and so on. But as we have seen, for instance, 1 by 3, there are many real numbers which has infinitely many digits in the mantissa. For instance, as I told you, 1 by 3, which is actually like this. In the floating point representation, it is given like this, and it has infinitely many digits in the mantissa. But if you want to write it as a n-digit floating point representation, then you have to stop these digits up to n number of digits, depending on whatever n that we give, right? Thereby, we are only giving an approximation to the number 1 by 3. Okay, so that is called the floating point approximation. Later we will see that there are two ways that we can obtain a floating point approximation of a given real number. One is by rounding and another is by chopping. Before getting into that, let us also introduce one more important point, that is regarding the memory overflow and underflow. When a value is stored in the computer, as we know, computer has only finite precision memory. Often, if you try to store a number which is much bigger than its capacity, there is also a danger. If you are storing a number whose value is very large, then also this computer will struggle to store it, and that is called the overflow. If you recall, in the floating point representation, you have mantissa and you have the exponent, right? If the number of the mantissa digits are more than the precision, then the computer just makes a approximation of that number. So that is floating point approximation. And if the number itself is so big, like I'm trying to store a number which is 3, 4, 7, 3, 2, 6, 8, 4, 5, 9, like that, it goes on, say some 100 digits are there. Okay, it keeps on going up to some 100 digits, so big number, we don't know how to say that. Then how will you put it in the floating point representation? Well, it is minus 1s into, now in the mantissa, it will come as, you have to put 0.3473268 like that. It goes on so many. All that has to be pushed before the decimal point. Therefore, 10 to the power of something like big number like 100 or something, right? So a big number you have to give as the exponent. Generally, computers have limitation to handle a big number in terms of the exponent also. Not only in terms of the mantissa, it also depends on how big this exponent is. When the value of the exponent in a floating point number exceeds the maximum limit of the memory, we counter the overflow of memory. Similarly, if you have a number which is 0.000, so many zeros, and then say some 1,000 zeros, and then 3143 like that you have, then its floating point representation is again, you have to throw off all these zeros. Say there are 1,000 zeros and then this, then it is 3143 into 10 to the power of minus 1,000 will come, right? Again, your computer has limitation to store this smaller value of the exponent also. So it has its own limitation of what the E that comes out in the floating point representation of that number. If it is too small, then we say that underflow happened. And if that E is too big, we say that overflow of memory happened. So generally, if you take a computer processor, the processor manual will tell you what is the lower bound and the upper bound of the exponent that your computer can handle. As I told you, during the calculation, number has a exponent E greater than that limit, whatever the processor fixes. we say that overflow occurs. And similarly, when E is less than the lower bound of the exponent, we say that the memory underflow occurs. In the case of overflow of memory in a floating point number, a computer will usually produce meaningless results or simply prints the symbol INF. It means infinity. So if you are trying to give a number to your computer for which the exponent is too large, that overflow of memory happens, it considers that number as infinity. Although for a human being it may not be infinity, but for the computer it will be infinity. If you would have worked in some scientific computing, you would have often seen this symbol NaN. It means not a number. This happens especially when your computer is trying to do this kind of calculations, 0 by 0, infinity by infinity, and so on. I think in calculus also we come across such symbols. The underflow is more serious when compared to overflow, because in this case, computer simply consider the number as 0. That is, when you are trying to give a number whose exponent in the floating point representation is smaller than the lower limit of the computer's processor that it can handle. That is, if the underflow happens, then the computer simply consider that number as 0 and then it goes on with the calculation. See how dangerous it is. If the overflow happens, the computer will start producing these kind of symbols. Therefore, in your answer, you will see in for NaN. That itself is a warning that something went wrong in the calculation. Whereas, suppose in a very big expression, you are giving many numbers and trying to calculate the value of that expression. In that, if one of the number was so small that the underflow happened and your computer simply put that number as 0 and calculated it, you will not even realize that there was a underflow happened, because you don't see any such unusual symbols in your answer. That is why underflow is more serious. You may not be knowing often that there was an underflow happened in your calculation. So you have to be very careful with this underflows. The next notion is the precision. The number of digits n in the mantissa, as given in the definition of the n-digit floating point representation, is called the precision or the length of the floating point number. A computing device will have its own limitation on the length of the mantissa. If a given real number has infinitely many digits in the mantissa of the floating point form, then the computing device converts this number into n-digit floating point form. That n depends on what is the precision that we give. Generally, in the programming languages, we have choice to fix single precision and double precision. They all have their own value of n. So whenever we work in either the double precision or single precision, the computer will try to restrict the number of digits in the mantissa to the n that is prescribed. Such an approximation is called the floating point approximation of a real number. So generally this is done by discarding the digits after nth digit in the mantissa in some sense. How a computer does this conversion is a characteristic of the computing device itself. We will not discuss these things in detail, but we will take two such conversion algorithm in their simplest form. One is the chopping algorithm and other is rounding one. They have their own elaborate algorithm. Generally, most of the processors use rounding algorithm, but here for the mathematical purpose, we will consider them in a simple form. Let's put it as a definition. Let x be a real number given in the floating point representation like this. What is meant by chopped approximation of x is simply you take this part in the mantissa and just forget this part. That is called the chopping approximation. What is meant by the rounding approximation? Well, there are some complicated algorithms for efficient and more accurate rounding, but we will consider a simple form of it, where if the dn plus 1, that is this digit, is between 0 and beta by 2, just keep 10 in mind. If it is 0 to 5, then we just use the chopping algorithm. If it is from beta by 2 to beta, in the case of 10, it is 5 to 10, we will add 1 to the digit dn, and that is generally what we will call as rounding approximation of x. So the rounding can be done also like this, but it is very simple to understand, therefore I don't need to explain this. Let's give an example. The number pi has an infinite decimal digit of the form 3.1415 and so on. We all know this. This number can be written in the floating point representation like this. And now, if you want to do a 5-digit chopping, what you do is you just simply count 1, 2, 3, 4, 5 and take this much in the mantissa and forget the other digit. That is the 5-point chopping. Similarly, any number n if I give, you can do the chopping of that real number. So the 5-digit rounding is given by this. Why? Because we take up to here. In rounding, we will take the dn plus 1th digit and see if it is between 0 to beta by 2. Since we are working with decimal, therefore this is 5, then we will just take the chopping. Otherwise, we will add 1 to the previous one. Since here we have 9, which is greater than 5, we will add 1 to dn, that is 5. Therefore, 5-digit rounding approximation gives us the mantissa as 31416, because we are adding 1 to 5, given that the next digit was 9. This is just a remark. Most of the modern processors, including Intel and so on, they use 52 digits in mantissa, 64-bit binary representation, 11 bits in the exponents, and 1 bit for sign. This representation is called the double precision number. We generally will not give much weightage on this kind of technical parts from the computer's point of view. We only consider the mathematical aspects of the rounding and chopping, and how this rounding and chopping approximation propagates in our calculations and affect the entire calculation. That is what is our aim. And our aim is not to get into the technicals of the computers. When we perform a computation without any floating point approximation, we say the computation is done using infinite precision. So from the examination point of view, if I say you do the calculation with infinite precision, then probably you can keep every number in the expression in the fractional form. Like for instance, 2 by 3 plus 6 by 5, I want you to do with infinite precision. Then you do with the fractional form itself. If I say you do this calculation with 5-digit rounding, then 2 by 3, you should write it in the floating point form, that is minus 1 to the power of 0 into 0.1, 2, 3, 4, 5, 6, and then the other one is 6, therefore it will be 7. So if I say 5-digit rounding, you have to do like this, and similarly 6.5 is approximately equal to, so well here it's nice, 0.12 only, there is no approximation here, into 10 to the power of 1. And then you do the addition and give the final answer again by making a 5-digit rounding. This is what you have to do. Whereas if I say it is infinite precision, then you do the direct calculation with the fractional form of the numbers.